Welcome to the lecture video for section 3.5 on Taylor series, in which we combine everything we've learned so far, or most of the things we've learned in this class, namely sequences and series, that being infinite series, and some calculus about functions and power series that we learned about in the last lecture video. So the notion of a Taylor series is a type of power series that represents a real value function f of x. And we're going to use a few different techniques to handle these. In some sense, it will feel easier to work with Taylor series than Taylor polynomials and power series individually, because we, in some sense, already know what the answer is. We know it's representing a function, and we know lots and lots of things about real valued functions from earlier calculus sections. So the main two goals are to learn about Taylor series by combining techniques from power series and from general algebra tricks that we use to work with polynomials and functions. And we'll also learn how to integrate and differentiate power series in this new format of a Taylor series. We already saw some hints about goal number 2 in the last video, so this won't feel too new about anything. We're just putting a lot of things and combining our efforts together. So what is a Taylor series? This is the main definition for this, really for this whole chapter in the book. The Taylor series of a function f of x centered at x equals a is the following nasty looking formula. So I want to spend some time and look at this expression. It's a summation from k equals 0 to infinity. So that means it's an infinite series. The terms here actually don't look too bad because they look like the terms of our Taylor polynomials. So let me just read out what the expression is in the summation formula. It's the kth derivative f upper k at x equals a divided by k factorial, all of this multiplied by x minus a raised to the k power. So I want to say two things about this. Yes, these are the coefficients or the terms of the Taylor polynomials Tn for this same function centered at the same value x equals a. So the formula is actually something we already know. We're just putting a summation from k equals 0 to infinity instead of up to a finite value n. And that's really the only difference between our sequence of Taylor polynomials, which are used to sequentially approximate our function f of x, and this entire gadget called the Taylor series. On the other hand, because we learned in lecture 3.4 what a power series is, it's a collection of infinite series that are functions of that are a single function of x, and each value of x that we plug in gives a different infinite series. We can also view a Taylor series not as the collection of Taylor polynomials, which is useful, but as a power series, which may or may not converge for different values of x. So on one hand, we'll use this to capture all Taylor polynomial approximations at a single time, and if we want, we can chop this summation off at a finite number of terms and use that to approximate our function. And on the other hand, we will know things about this because it is a power series, and we now have convergence detection techniques such as the ratio test or the geometric series test. These are really powerful gadgets, and I would wager that the Taylor series is the most useful of all of the objects or all of the different concepts you've learned in calculus. And this really includes, in some sense, derivatives and integrals, although derivatives are used to define the Taylor series. You see them appear here. In terms of what Taylor series can do for approximating and for actually computing things, they're really powerful tools. And they're also just pretty cool once you get to know how to work with them. So a remark about terminology: Taylor is named for a mathematician, and the specific kind of Taylor series where the center is x equals 0, namely the terms will just look like x raised to the k power when we plug in a equals 0. These were popularized by a different mathematician around the same time. Maclaurin was his name, so Maclaurin series is the name we give to any Taylor series centered at a equals 0. So I'll be using the term Maclaurin series to mean the one centered at a equals 0, and in general, we'll be looking at Taylor series for different a values in this video. You'll see some examples of both. There are some, even before we do any examples, there are some limitations to what we can do with Taylor series. You might recall the example that's shown near the bottom of the slide, this piecewise defined function, which for the positive real numbers is given by e to the minus 1 over x, and then for the negative numbers and 0, it's just given by the horizontal line y equals 0. Because of the nature of the derivatives of this function, and you can compute higher and higher derivatives of f of x, and at 0 you will always get 0, the Taylor approximations, the Taylor polynomial approximations will always be the 0 polynomial. You'll have no non-zero terms in front of the higher powers of x. And that means that the Taylor series, which is again the power series built out of those those Taylor polynomial partial sums will not actually tell you anything. It's just a horizontal line, and clearly for small enough values of x close to 0, but in general, just for different values of x away from the negative ones where the function's equal to 0, this function will not be the Taylor series will not converge to the true value of this function, and that's an issue. But we're not going to see too many examples like this in this course. Let's jump right in and do an example. This might become your favorite example because we actually already know all of the terms. The real key here is we know all of the derivatives of f of x equals e to the x. They're just e to the x again, so it's easy to evaluate them, come up with the coefficients for the Taylor series, and then jump straight into the question of how fast it converges, and where does it converge and how fast it converges. So let's work it through. If this is one you want to try on your own, this might be the best opportunity for you to do a problem completely from scratch. So don't look at what's on the screen if you want to pause the video now. But if you're ready to do this one together, I'm first going to do part A, find the Taylor series for f of x centered at x equals 0. Well, we already did a lot of work for this problem because we previously computed together the nth Taylor polynomial for this function e to the x centered at 0. And in summation symbols, this looked like the sum from k equals 0 to n to get a degree n polynomial. The coefficients were 1 over k factorial. This just comes from setting all of the derivatives at 0 equal to 1 in the numerator, times the power of x, which is x to the k. So this will give you a polynomial that starts 1 plus x plus 1/2 x squared, and then it ends up with a final term of 1 over n factorial times x to the n. If these are the partial sums of our infinite Taylor series, or in this case, I'll say Maclaurin series, since we're centered at 0, then the full Maclaurin series is we're literally just going to put an infinity in place of that n. That's what it means to take the limit or the infinite sum of these finite polynomials. I'm going to stick an infinity up there. I'll copy the same formula, 1 over k factorial times x to the k. And just to show you what it looks like, I already wrote out a few terms. 1 plus x plus 1/2 x squared. The next one, by the way, is 1/6 x cubed. And then it keeps getting, the denominators keep getting larger from there. They're just the factorial sequence, and then the powers of x get larger. So this is a function in its power series. Maybe for the moment, we'll call this t of x. And in the next part, I want to ask, for what x values does this series converge? If the power series converges, so if we plug in an x value, that gives us a single infinite series with just numbers in the coefficients. And if that infinite series converges, we say that, again, the power series converges at that x value. If it does, it's going to converge to e to the x. This is essentially by the Taylor inequality, or Taylor's remainder theorem, that says if the bound on our error goes to 0, then the sequence of polynomials, in this case grouped together as the Maclaurin series, will converge to that value of f of x. So on what interval does this does this Maclaurin series converge? And I put, since the power series is not a geometric power series, since I don't just have a times x to the k, I have coefficients that are changing here in front of x to the k. I can't use my geometric series test. However, we can use the ratio test. And you will find, after doing a number of these problems on your own, that the ratio test is extremely useful for power series and for Taylor and Maclaurin series. So in the ratio test, we need to compute the following expression that we call capital L. It's a limit as k approaches infinity of, in words, the ratio between subsequent expressions or subsequent terms in our power series. So I'm going to write it as a k plus 1 over a k. And remember, we want to take an absolute value to get a positive number or 0, and check if this expression is bigger than or smaller than 1. So let's plug in what the terms of the power series look like. And I'm not going to scroll up. We can look at your notes to double check, but the k plus first term will look like 1 over k plus 1 factorial times x to the k plus 1. And the kth expression is the same thing with just k instead of k plus 1. I'm going to leave absolute values here because the x values that show up in this fraction could be positive or negative. So we actually need some absolute values to hang around. Let's keep our limit symbol out front. And like I've done in other examples, I'm going to group like terms. I'm going to skip a step here where I flip the fraction over in the denominator to make it the reciprocal in the numerator. And I'm just going to group together what I see. So we'll end up with a k factorial in the numerator, and then I have a k plus 1 factorial in the denominator. That's grouping together these expressions. And then on the other hand, I have an x to the k plus 1 and an x to the k. And I'm going to leave my absolute values around that. X to the k plus 1 is in the numerator, x to the k will stay in the denominator. Good. So that's usually step 1, or rather step 1 is write a to the ak plus 1 over ak. And then part of step 1 or step 2, whatever you want to number these as, is separate out like terms and group them together. The next step, the important one, is let's simplify this expression so we can take a limit. Well, the nifty thing about factorials is if I have subsequent factorials, a lot of terms cancel out, and I'll just be left with a k plus 1 in the denominator. If you forget why that's true, just remind yourself of the definition of factorial and reason through that step on your own. Next, I have an x to the k plus 1 and an x to the k, so most of my powers of x drop out. I'm just left with x to the 1. And I'll leave that in absolute values. Well, here's the miracle. Whatever x value I plug in, I'm going to stick that in and then ask for the limit as k goes to infinity. No matter what real number I plug in here, the denominator is getting larger. So this whole expression goes to 0. So again, this was L. And we see that L is 0, which is less than 1. So take a moment and remind yourself, here are the options for the ratio test, by the way. Does the power series converge or diverge based on that ratio test? And for any power series, we had a theorem that said these are the only possible options. So for any x value, we got L is 0, no matter what the x we plugged in, which is less than 1. And when the L value is less than 1 in the ratio test, the series converges. So what we actually just proved is that for any x value, the series converges, which means that the function e to the x is identical to its Taylor polynomial, or sorry, its Taylor series, its Maclaurin series, the sum from 0 to infinity, 1 over k factorial x to the k. And in the future, we can actually think, so we're going to equate these two things. We can think of these as the same function. E to the x is identically equal to k equals 0 to infinity, 1 over k factorial, 1 over k factorial x to the k. These are the same function. How do we know that? If I plug in any x value, the thing on the right converges, and the Taylor inequality, the Taylor remainder theorem tells us that the difference between these two expressions goes to 0. So they have to be the same function when we take k to go to infinity. Great. There's another example below, but let's get there in time. We've got a few more slides to go through before that. Maybe it's next. Hold on. Nope, never mind. It's next up. So here's a big long slide. You can pause to read each piece before I get into the problem part by part, but I'm just going to jump straight back over and start working through each piece. The goal in this problem is to say something about the Taylor series for ln of x, and we're going to center it at a different place. So this is a true Taylor series, not a Maclaurin series. You'll see in part B, we're centering this, the polynomials and the function at x equals 1. This one technically is one that you can work through yourself. You have the techniques in order to solve this problem, but to find a pattern for the derivatives, I've done it the old-fashioned way by writing out everything by hand, and we'll just do a bit of pattern recognition together. This would be a thing that you could write down carefully by yourself, but it gets a little tedious after a while. So I've written them out ahead of time. And in part A of the problem, we're asked to find a pattern in the derivatives to come up with a formula for fk of x, the kth derivative. Well, here are some derivatives. And let's just talk it through. The 0th derivative is just the original function, that's ln of x. But as soon as we start hitting this nail with our derivative hammer, we'll see familiar expressions popping out. The first derivative is 1 over x. And after that, we get subsequent powers of x in the denominator that go -1 over x squared, 2 over x cubed, -6 over x to the fourth, 24 over x to the fifth, and you can keep going from there if you need more terms to recognize the pattern. So this is why we practice with sequences. Can we recognize a pattern for the kth term in this table, which is the kth term in the sequence of derivatives for ln of x? And let's start in the denominator. What happens when I take k derivatives? Sure enough, I have that same power of x in the denominator every time. You'll see that there's a 1, a 2, a 3, a 4, a 5 corresponding to that k value. So it looks like I have x to the k in the denominator. The numerator is a little more complicated, and there are two things that I want to isolate. First of all, there's a sign flipper. It goes plus, minus, plus, minus. So we always use -1 raised to a power to accomplish this. And we just need to use raised to the k or the k plus 1, depending on where we want to start. If I plug in k equals 1, I should get a positive value. So I'm going to start at, with k equals 1, I'm going to give it the exponent, -1 to the k plus 1. This is something where there's only two options, because either we're starting at an even or an odd by plugging in the first k value, or we're starting at a plus or minus. So you just need to take a guess and tweak it if necessary. On the other hand, the remaining positive part of the coefficient goes 1, 1, 2, 6, 24. Hopefully by now that sounds familiar to you. That's exactly the factorial sequence, but the key is where we start here. And if you want, we know they're factorials of something. Let's just look at the most advanced one in the sequence, 24, or 6 if you prefer. This is 6 is 3 factorial and 24 is 4 factorial. And notice that it's shifted by 1 from our k value on the left of the table. So it looks like we're using the expression k minus 1 factorial times the sign flipper divided by the right power of x to get our kth derivative. So good news, you now know all derivatives of the function ln of x just by pattern recognition. If you wanted to evaluate these derivatives at any value, you can just plug x values into this formula, and you should know what k is in order to get an actual value of that derivative. But here's the beauty of this problem, or this dive into the function ln of x using Taylor series. If we want to write out Taylor polynomials, and ultimately those will form the Taylor series T of x for ln of x, let's center it at 1. Notice that I can't center at 0 in the form of Maclaurin series because ln of x has a vertical asymptote at x equals 0. So we're not even going to bother with that place. Instead, if we center at x equals 1, we just wrote down a formula for the kth derivative of this function. And the coefficients of a Taylor series, since it's the infinite expansion or the infinite summation of the Taylor polynomial terms, is obtained by plugging in x equals 1 into this formula and dividing by k factorial. So let's do that carefully together. So if I plug in, I'm only plugging in anything where I see an x. I'm not changing anything else in the formula. So I have a 1 to the k, which is just 1, and we'll drop it out completely, and then we still have to divide by k factorial. The real trick here is, can we simplify this expression, if possible? Well, yeah, I see subsequent factorials in a fraction, so I have one more expression or one more term in the denominator, and this is the ultimate expression that I'll get. I'll just have a single k, and the rest of the factorial expressions cancel each other out. So let's write down a formula for the Taylor series Tx of this function ln of x, centered at 1. The coefficients are these fellows that we just wrote down, and the formula reduced to -1 to k plus 1 divided by k. So that's what we call the coefficient. That's the numerical part with just k in the formula out front. And then because it's a Taylor series, we'll have x minus the center, which is here given by a equals 1, raised to the kth power. I pointed to the fact that I started at k equals 1 instead of k equals 0. If k equals 0, we have a problem because we can't divide by 0. But I want you to think carefully about actually why this makes sense to start at k equals 1, even though the general definition a few slides ago started at k equals 0. What do the terms of a Taylor series mean? Think about Taylor polynomials in particular. Okay, well, let's just keep plowing ahead and talk about convergence of this Taylor series. Let's see where the series converges. So if we perform the ratio test on the previous expression, again, it's a limit as k goes to infinity of the absolute value of the ratio of subsequent terms. And let's write down those subsequent terms. -1 to the k plus 1 is -1 to k plus 2 over k plus 1 times x minus 1 to the k plus 1. That's the numerator of our whole expression. And then I'll do the same thing with just k plugged in. Good. And we need to keep absolute values around. You see some plus minus, and you also see some x minus 1 stuff. And those could be positive or negative, depending on where we choose our x values. So let's perform the next step, which is group like terms. I'm actually going to completely, well, let's do it in a careful step. So I have a -1 to the k plus 2 and a -1 to the k plus 1. And this number is actually always equal to -1 on the nose. If you cancel out powers and just write -1 a single time, you'll see this explicitly. But I'm taking an absolute value. So in a moment, that'll just wipe out and become +1. Next, I see my just denominators of k. And if I move up this denominator to the numerator, it'll become, well, it'll go to the numerator and we'll get k over k plus 1 for the next expression. And looking ahead, when we take k to go to infinity and we do the highest power trick, this will go to 1. So we have 2 expressions going to 1. And finally, we'll be left with x minus 1 to the k plus 1 over x minus 1 to the k, and we can cancel powers there. So I'm going to do everything in one step next. Let's use some different colors. This whole expression we said is equal to -1, but we're taking the absolute value, so it becomes 1. And actually, let me rewrite that. I don't mean that this converges to 1. This is equal to +1, the whole expression. Next, k over k plus 1 as k goes to infinity goes to +1. So that one actually does require computing the limit. And then the last expression reduces to just x minus 1. There's an additional power in the numerator. So the k's go away. Nothing happens when we take the limit. We get x minus 1 in absolute value. So let's think about what the ratio test says. It says that our L value, which we just computed, again, this is L, is x minus 1 in absolute values. The power series converges, and in this case, it'll converge to the function ln of x when x minus 1 in absolute value, which is our L value, is less than 1. So let's write this out explicitly. So x minus 1 being less than 1 means that the distance of our x values away from x minus 1, or rather the distance between x and 1 is at most 1, or is strictly less than 1. We can write this out as a pair of inequalities like this, and then we can solve for x in the middle by adding 1 everywhere. So on the interval 0 to 2, I'll leave it with open parentheses because we don't know anything at the endpoints at the moment. This series converges, and it converges to ln of x. There's another way to come about this interval 0 to 2. So we now know 2 things. Using the terminology from the last video, we know that the interval of convergence of the Taylor series for ln of x centered at 1, the interval is 0 to 2. That also tells you that the radius of convergence is 1. You can think of the radius of convergence as the distance to the left or to the right of the center, in this case 1, that you can travel and stay within the radius of the interval of convergence. By the way, another way to compute the radius of convergence, if you know the interval, is to take the length of the interval and divide by 2. So the radius of convergence in general will be 2 minus 0. It'll be b minus a over 2, which is 1. There's another way to come about this interval of convergence from 0 to 2, which is a little more complicated, but it actually uses Taylor's inequality and the Taylor remainder theorem, which we can use to bound the error values in our approximations if we were just using Taylor polynomials. So let's recall our n plus first derivative. Well, our kth derivative look like, let's scroll up and go find it again. It was the sign flipper times k minus 1 factorial over x to the k. So if I plug in n plus 1 for k, I'll get -1 Now, technically, I should have to the n plus 2, but if you think about it, I can pull out two negative ones, and that's just a positive one. I just want to write this a little simpler here. Times, so if it was k minus 1 factorial, and here I'm plugging in n plus 1, so that'll give us an n factorial all over x to the n plus 1. Let me center that a little better. So this is, again, we want to bound the absolute value in order to use Taylor's inequality. That'll be our capital N, or our capital M bound. So here's what the function looks like on any interval, what the n plus first derivative looks like. If I apply the absolute values, n factorial is always positive. X, well, we're only looking at the ln function on its domain, which we're going to start breaking things up for bigger than and smaller than 1. But the only values we're allowed to plug into the ln function are positive anyways. So actually, I can completely drop my absolute values once I wipe out the -1 sign flipper. So this is what the absolute value of the n plus first derivative looks like. And we're going to start by looking at intervals from x up to 1, where x is between 0 and 1. So we're going to look at intervals of values that are smaller than 1. And looking at this function, well, it's just a fraction, so we can just analyze this directly. If we increase x, which increases the denominator, and we're not changing n for this estimation, then we will decrease the fraction. So this entire expression is decreasing on the interval x to 1. And I wrote down all three possibilities to remind you that if it's increasing or decreasing, we can immediately write down a bound, capital M. But if you can't see that this n plus first derivative is increasing or decreasing on the entire interval you're looking at, you will need to use optimization to find the maximum value on that interval that you're considering. In this case, we get lucky. And if we're looking on the interval from x to 1, then the maximum value is, with a decreasing function, will occur at the left endpoint, or at x. So in fact, we'll just get n factorial over x to the n plus 1 as our n value. Now that still involves x, so that's a little annoying, but we'll see how that fleshes out in a moment when we compute the Taylor inequality. Okay, so we have a bound, capital M. This is part D of the problem, for the absolute value of the n plus first derivative on intervals smaller than 1. What happens when we go up to intervals larger than 1? Well, if you look at our formula for the n plus first derivative, the fact that it was decreasing didn't really matter, or didn't depend on whether or not we were larger or smaller than 1. So the function here, the n plus first derivative, is still decreasing. And in this case, if it's decreasing, it achieves its largest value at x equals 1, in which case we will just get, so let's take a look at the derivative again. The absolute values were n factorial over x to the n plus 1. If I plug in x equals 1, I'll just get an n factorial. I left a little room. This is why I wanted to remind myself it's this over 1 to the n plus 1. That's simply n factorial. So this gives us a new bound on the derivatives when we're looking at x values larger than 1. If this is a little confusing, then this is the reason that we had that ratio test to verify things for us. It works a little bit faster, but this is the approximate version that we can use to actually generate approximations with certain accuracy. So finally, let's start stitching things together. What does Taylor's inequality say about the error, that Rn remainder expression, as n goes to infinity? Well, first of all, for x values less than 1, we know that the Taylor inequality always looks like this, just to remind you. Rn is bounded in absolute value by that derivative bound m times x minus 1 to the n plus 1 over n plus 1 factorial. Let's plug in the value that we got for m. And for the first part, for part D of the problem, the m value we chose was n factorial over x to the n plus 1. So we're going to have n factorial over x to the n plus 1 times x minus 1 to the n plus 1 over n plus 1 factorial. And just like I do with the ratio test, I'm going to group like terms here. And you'll see I'm going to also do things a little bit faster, but you should write out every step if you haven't practiced this too much. My factorial expression, I have n factorial over n plus 1 factorial, and that will reduce to just n plus 1 in the denominator. On the other hand, I have an x minus 1 to the n plus 1 and an x to the n plus 1. So I'm going to group these together in absolute values as such. Now, as long as I'm plugging in values that are where x is positive, this expression is going to go to 0, including when we plug in, what would be the only issue here? I believe 1/2 is an issue, and I didn't write this out very carefully, but you'll see it in the textbook that 1/2 is sort of a different case. Even if you plug in, basically what's going to happen is no matter what you plug in here, it's going to be small enough so that the exponent takes you to takes you down to 0 rather than up to infinity. Oh, I know what it is. If you plug in 2, no, even 2 works. I think it is 1/2 that makes this expression look suspect. But in that case, the n plus 1 will take over and take you down to 0. In any case, this always goes to 0. As long as x minus 1 is going to be less than 1. Basically, as long as we're within 1 unit of the center. We can't go further left than that past 0 because of domain issues with the ln function. So on the interval from 0 to 1, our capital M expression gave us a Taylor remainder going to 0. Things are a little bit easier to analyze when x is larger than 1. In this case, our m value, I'm not going to scroll up, but you can go check. It was just n factorial. Okay, and in this case, our whole expression, again, there's a cancellation among the factorials, and then we'll just have x minus 1 raised to the n plus 1. Here we have to do a little more analysis. So the bound was easier to write down. It simplifies a little bit easier. And the idea here is this is just powers of n in the denominator, and anything exponential will beat it as long as, well, it's going to beat it no matter what, right? So if this expression inside of the absolute values is greater than 1, then this expression is going to blow up and take us off to infinity. So the only way for this to converge to 0, which is when the error goes to 0 or our approximations converge to the true value, is for x minus 1 to be less than or equal to 1. Notice that if x minus 1 is equal to 1, then this whole expression will just be a constant 1, and then the 1 over n plus 1 will take us to 0 as n goes to infinity anyways. But if you're not sure about that, just think carefully about the endpoint issues. Another way to write this says that x minus 1 is strictly between, or is between or including -1 and +1. And solving for x in the middle, I'll get 0 and 2. Now, we said x is greater than or equal to 1. We're already worried about x equals 0, but not to fear, this is really the part that matters. Because this was for x larger than 1 that we were able to use that Taylor inequality estimate. So this works on the interval from 1 to 2, and it actually looks like it includes 2. But I'm not going to say anything about 2 specifically. Well, yeah, no, it does look like it works at 2. So we'll say 2 as well. According to the Taylor estimate here, this works including 2. So what did we learn from the previous explorations, really the last 3 parts of this problem? We learned that the function t of x, which is a power series, converges on the interval from 0 to 2. When we just used the ratio test, it only told us from 0 to 2, not including the endpoints, but we in fact learned by analyzing the Taylor error remainders that we can include the right endpoint x equals 2, and it converges to the function ln of x on this interval. So way to go. We got through a pretty tough problem with some interesting Taylor inequality estimates to practice along the way. Let's wrap up a few more topics. We'll do another major Taylor series computation to practice in just a moment. So that was just slide by slide going through that. By the way, here's a graphical depiction, and I really, really like Taylor series for this reason, that they're extremely satisfying to graph, and then to take larger and larger, or rather the Taylor polynomials are fun to graph, and then to take larger and larger degrees and see that we'll start hugging the red function, or rather the blue curve is y equals ln of x closer and closer as we take higher degrees here. In other words, the sequence of Taylor polynomials will start to converge to our function, at least on the interval from 0 to 2. If you go and click on the interactive version of these slides, you can play around with the slider bar here. There's also a Desmos widget, and I believe Wolfram Alpha will let you do something with Taylor polynomials, but the Desmos one is probably the best, where you can just play around with this slider bar and put in really high values for the degrees of your Taylor polynomials, and you'll see that they start converging to the ln function, but only in the interval from 0 to 2, and we can't really predict anything outside of that interval. Okay, here's a new problem that we can try. And I want you to just think about this before we dive in and solve it together. What would you have to do to compute a Taylor series expression? And in this case, it's centered at 0, so we can call it a Maclaurin series for the function x squared times sine of x. What would you do to find the terms of the Taylor series at 0 for x squared sine of x? While you're thinking about that, I'm going to take a drink of water, and then we'll explore this together. Okay, let's get into it. So part of your answer for this, if you were brainstorming, might have been, well, we would need to start computing some derivatives like we did for ln and for e, and try to recognize a pattern in the derivatives, or at least their values at 0, and then try to start computing things that way. I don't encourage that in this case. So that's a good way to practice computing derivative tables and just kind of work through things by hand and work on pattern recognition. But if your goal is to come up with a Taylor series as quickly as possible, then there's a better approach, which is to remember something about the sine of x function, and then later we'll incorporate the x squared separately once we know about the sine function. So one thing that we worked through together in a previous lecture video, the Taylor polynomial lecture, was finding the coefficients for the Taylor polynomials for the function, I'll call it g of x just temporarily, sine of x, centered at x equals 0. And they all looked like they only had odd powers of x showing up. So the first term was x raised to the 1, and then there was minus 6, or minus, sorry, what is it? Minus, I should know this, minus 6x cubed. No, minus 1/6 x cubed is the next one, and so on and so forth. You can write them out using this formula. And in general, we'll group these together into the summation notation from the counter k equals 0 to n. N is not the degree of the polynomial. It's really 2n plus 1, as I indicated here, because the expression has coefficients -1 to the k, there's a sign flipper, divided by the 2k plus 1, that odd number factorial, times the odd degree x raised to the 2k plus 1. This is a bit of composing these patterns into a single formula that we worked on a while ago, but I'll just give you the Taylor polynomial here. Well, that means we know the Maclaurin series for sine of x because it's just this same expression, except we add up to infinity and beyond. So we'll start at k equals 0. We'll go up to infinity. That means we're going to include all odd degrees of x in this entire Taylor series expression, or Maclaurin series. We'll have the sign flipper. We'll divide by odd factorials, and we'll multiply by odd powers of x. That's how I try to remember the sine functions, all of the odd powers of x, and then you just need to remember a little bit about what the coefficients look like. By the way, cosine of x has a very similar expression, where instead of odd, we use the even powers and the even factorials in the denominator. Otherwise, it's identical. So in order to get a Maclaurin series for our function, which was x squared times sine of x, let's start with the Maclaurin series we already know for sine of x, and then just multiply through by x squared and see what happens. So if I take x squared and I multiply by this whole, I'm on a tablet, I can copy paste. I multiply through by this whole ghastly looking thing here. How can we possibly come up with a Maclaurin series for f of x? Well, let's just take our x squared up front and distribute it term by term. And this is what's amazing about power series. This is one of the tricks that we'll learn that makes power series really nifty, is we're just inserting new powers of x, we can just change the formula accordingly. So there's nothing here with x's, I'll leave that the same. And here if I have x to the 2k plus 1, and I want to multiply by 2 additional powers of x, then I'll get 2k plus 3 as the new power. If you want to double check that this formula is correct, I encourage you to write out the first few expressions for the Maclaurin series for sine based on our formula, and then multiply, basically FOIL it out, distribute the x squared into each term, and see that this formula is exactly the one that captures that new expression. So the summary here is, if we have powers of x we want to multiply by our function, rather than computing complicated product rule derivatives, we can form the original Maclaurin series, or in general Taylor series, and then directly multiply term by term. It's a really nice algebra trick. By the way, you can check by computing a few derivatives of x squared sine of x that those coefficients will match. So here's a more general formula. It's basically what we just said. If we have some function f of x, which is of the form x to the k times g of x, and it has to be centered at 0 for this trick to work. I'll let you think about what would happen if it were centered somewhere else. But if we have that expression, first construct the Taylor series for g of x, and then distribute the extra powers of x, these x to the k, into the formula directly. Here's another type of trick, and this is really where Taylor polynomial or Taylor series start taking off and becoming even more useful than some calculus techniques we've learned. We can write Taylor series down for functions that we've had trouble performing calculus on in the past. I'm going to skip ahead just to point out in part C that our goal in this problem is to compute a Taylor series for the indefinite integral of e to the x squared dx. This expression shows up in our probability section as a particular, or adjusting by some coefficients, a particular type of probability density function. And I believe I said in that video that we don't know how to integrate this function. I definitely mentioned in the integration by parts video that there are some integrals we just cannot solve, no matter what techniques we throw at them. And this is one where there's no closed form solution. There's no nice functional equation for the integral of e to the x squared. However, we can still expand that expression using our knowledge of Taylor series and integration of power series from the last video lecture. So let's get started on this one together. It would be a good idea to practice, before I scroll down and reveal anything, the first part of the problem, which is to write a Taylor polynomial T4 for the function e to the x squared centered at x equals 0. I really encourage everyone to try to do this by hand. It's only 4 derivatives. There's going to be some product rules to evaluate, but it's good practice to write out the full table for yourself, because you certainly could have this on a quiz, maybe not with so many complicated terms, but on an exam when you have more time to think about it. So we're going to do T4 together, and I'm scrolling down, so pause the video if you don't want to be spoiled, if you don't want to have it spoiled. Here's the table that I've already written out with up to the 4th derivative of e to the x squared. And again, I had to carefully compute using the product rule starting when I went from the 1st to the 2nd derivative. There's also a chain rule in basically every step. And the nice thing is when I plug in x equals 0, a lot of things simplify dramatically. Basically, any e to the x squared term will be 1, and any polynomial term will be 0 unless it doesn't have a power of x. So I'm actually only writing the coefficients of the Maclaurin series over here. I'm directly making the evaluation at x equals 0, and then also dividing by k factorial just to move things along. And I really didn't have much room for a 4th column anyways. But here, the terms go 1, 0, 1, 0, 1 half. I don't really know what a pattern is for that yet. I don't really have enough terms to truly evaluate that, but I see that it looks like the odd expressions, the odd terms will be 0. So at least I'm only looking for even powers of x. And if all I wanted to do was to write down the 4th Taylor polynomial, I could do that. The constant term is 1 times x to the 0. There's no x to the 1 term. The x squared term is 1 times x squared. There's no x cubed term. And then the 4th term is 1 half x to the 4th. And if I said come up with an expression for Tn, the nth Taylor polynomial, we don't have enough information yet. That's really not enough for me to detect a pattern. Unless you're thinking factorials, which maybe it is, if we said this is 1 over 1, 1 over 1, 1 over 2, then, if we go up and compute the 6th derivative and check that the next one should be 1 over 6, then that would probably confirm the pattern. But in any case, let's do part B of this problem and use a different algebraic trick. It's not the same as multiplying by new powers of x on the outside. It's the substitution trick, which we haven't learned yet, but I'm teaching you this on the fly as we do this example. So a better way to find a Taylor series is to observe that this function is related in some way to a more familiar function whose Maclaurin series we already know. Namely, f of x, which is e to the x squared, can be written as g of x squared. This is a composition of functions, or we substituted an x squared into the g function, where g of x is just e to the x. So let's take our Maclaurin series for g of x, that's e to the x, which we already wrote down at the top of this video. Here it is again. The sum from 0 to infinity of 1 over k factorial x to the k. And now rather than multiplying additional powers of x in, we're going to directly substitute in for x and replace every x I see with an x squared. And this will give us the Maclaurin series for e to the x squared, which I think is amazing that you can do this. I'm not justifying any of the math why this is truly the Maclaurin series, but it's something you would do in a different calc course, and you can look up the details online if you're curious. So the Maclaurin series for f of x, let's write that this is equal to g of x. And in fact, that we know that this is equal to g of x on the entire real number line by the first problem that we did together today. The e to the x series converges everywhere. Let's next substitute in x squared to get our expression for f of x, which again is e to the x squared. This is going to be equal to summation from k equals 0 to infinity 1 over k factorial, and I'm putting in an x squared everywhere, so that'll give me even powers of x to the 2k. And you know what? Sure enough, this recovers the fourth Taylor polynomial that we came up with together. If you start writing out terms, you'll see it's 1 plus x squared plus 1/2 x to the fourth. And sure enough, I was not lying when I said 1/6 x to the sixth was the next even term in the sequence of polynomials. This gives you a much faster way of doing that without having to compute any additional derivatives once you already know the e to the x expression. But we can still do more calculus on this expression. So now we have f of x, our e to the x squared Maclaurin series. And if we want to integrate a power series, we learned how to do this. The name of the game is power series are sort of like polynomials. You can think of them as limits of polynomials or infinite polynomials, infinite summations. And the calculus theorem for differentiation and integration of power series we learned in the last video said, just do it term by term, do the power rule, pretend that it was actually a polynomial. So since e to the x squared is approximated by this expression, I'll copy paste it again. And we want to integrate e to the x squared. We're just going to integrate this whole expression term by term. It's going to be k equals 0 to infinity 1 over k factorial. And here's what we're going to do. I'm going to raise the power by 1, x to the 2k plus 1, and divide by the new power, which is 2k plus 1. So that's it. I'm actually going to rewrite this a little bit so it still looks like a power series, and even it looks like a Maclaurin series. And it'll look like 1 over 2k plus 1 times k factorial. So it's not the whole expression factorial, it's k factorial, multiply all those out, and then additionally 2k plus 1 times x to the 2k plus 1. If you wanted to see this explicitly and check that this formula is correct, I wrote out the first up to degree 6 for the whole Taylor series for e to the x squared. Just try integrating each of these individually, pretending that they're just terms in a polynomial using the power rule, and you'll see that we get the expression that I wrote down. Notice that the k counter stays starting at 0, but the powers of x go up because I added an additional power of x. So you could rewrite this a little differently if you wanted, but this is a fine enough expression for our purposes. So we worked out the Taylor series for this expression, and now you could ask things like, what happens if we integrate this expression from negative infinity to infinity? Well, this is, and actually, sorry, I probably should say, so if this is our antiderivative, I'll interrupt myself and say, here's our antiderivative. So the integral expression, to be very, very picky about this, is given by any antiderivative, namely this one, plus a constant term. So function, any antiderivative, namely that one, plus a constant term. If you wanted to integrate this function, we could integrate this function, from 0 to 5 if we really wanted to, and we could use the actual explicit Taylor polynomial or Taylor series to do that, or we could take approximate values for these integrals. This gives us a lot of information about this integral symbol that we didn't previously have, since we didn't originally know an antiderivative. This is what's called not a closed formula. A closed formula would be something like, x e to the x squared. Basically all of our fundamental real valued functions, I'll say like polynomial, all the stuff that shows up in the ILATE acronym. Those are kind of our basic types of functions, etc. Not one of these. So there's no actual closed formula in terms of functions we recognize for this antiderivative. And it's not just because you haven't learned about the functions yet. There's no way to write this. However, we can do all sorts of calculus on that. I'm going to stop the discussion here so we don't spend too much more time in this video. There's a couple things to wrap up at the end, but I encourage you to think about what it would look like to integrate this expression. What would it look like to integrate e to the x squared using the fundamental theorem of calculus, evaluating this new power series expression for the antiderivative at 0 and b and taking the limit as b goes to infinity. And we know that all of those power series exist because the original series converged for all real numbers, and the calculus theorem that allows us to integrate or differentiate says that the same interval of convergence holds for the new series. So to wrap things up, oh, by the way, here's a picture if you were curious about e to the x squared. The blue graph is that function. And as you slide the bar around, you'll see that we get interesting approximations using Taylor polynomials to the red function, which is the integral. And actually, I don't think it is the red one. This might be labeled wrong. You'll have to take a look at the interactive slider to see which ones change around. It's kind of hard in this picture for me to tell. Looks like the red one is actually the polynomial, and there's a yellow one hidden back there. That's the actual, a particular antiderivative of this function. Okay. So I'm not going to do this one with you, but I encourage you to think through this. This is just a little symbolic exercise using the imaginary number I. Remember that I is the square root of -1. Another way to think of this is that I squared equals -1. You can actually use the same techniques we've been doing the whole time, either multiplying by additional powers of x or substituting in for different functions to find a Taylor series expression for e to the ix, using the fact that I squared equals -1. What's a miracle in this case is in part B, if you work through this whole problem by yourself, the terms of that Taylor series in part A will appear as terms in the sine and cosine Maclaurin series. And if you write out e to the ix as a Taylor series and expand it using sine and cosine, and then rewrite those expressions as the relevant sine and cosine functions, you'll be able to relate the exponential expression e to the ix to sine and cosine, and you'll see that there's a really intimate relation between different values of these things. In particular, a very famous equation due to Euler happens when you plug in x equals 1. There's actually a couple that work out. X equals pi might be an interesting one to try as well. When you plug in certain values for x, namely x equals 1 or x equals pi, you'll get an interesting, sorry, actually it's x equals pi. I didn't mean to say x equals 1. When you plug in x equals pi, the expression for e to the I pi that you obtain in part B is a really famous equation that relates a bunch of different fundamental constants that we use in math class. Finally, part C is asking you to do something different. And how is this useful? I'll let you explore that on your own. To summarize, and I'll have one practice problem for you at the very end, I want you to reflect on the following concepts. How can we be sure that once we write a Taylor series down for our given function, that it converges to the function that we're supposed to approximate? Related to this, what is the domain of a Taylor series, and what does it mean to say that this is the domain of a Taylor series? Question 3 is, how can we produce the Taylor series for something of the form x to the n times f of x, or f of x to the n? Presumably, we already know the Taylor series for f of x. Where does the center of the series need for the result to actually give us a Taylor series? And finally, probably related to some other parts of this question, what is a Maclaurin series? When I say Maclaurin series, what does that mean? How do you know to recognize a Maclaurin series? Here's a practice problem for you to think about. This is a little more conceptual, but this will step you through some of the remainder going to zero types of conceptual features of these Taylor series problems. Thanks for tuning in, and I'll see you next time. I hope you enjoyed a tour through Taylor series in a single lecture.